So Professor Clements with you as we begin explore material in Chapter 21 of the OpenStax College Physics textbook. In this situation, we would like to determine the EMF of an unknown battery. So that's the EMF sub x. And we have a standard battery, so EMF sub s for standard. And we're going to use the technique of a null. We have a galvanometer here. We'll be adjusting a potentiometer, sliding this contact back and forth until the current in the galvanometer is 0. We do that for both the standard cell being in the circuit, and then we remove the standard cell and put an unknown cell in the circuit, unknown EMF. This analysis will rely on the concept of voltage, potential difference, equals current times resistance. So let's see how we proceed. We have a battery at the top here. We don't need to know the value of this battery or power supply, but we need some element of the circuit here that will maintain a constant EMF, a constant current through the system down here. Now we have a we'll get that up here again. The battery on the top branch, we want it to supply a nice steady current through the circuit. We don't need to know the value of the EMF of this top battery. So the standard EMF, when that's in place, and I'll lower this just a little bit, we adjust the potentiometer and we get the current to be 0 in the galvanometer. There'll be a resistance across here, R sub s. And in some situations we may use a real long wire across here and measure the length of the wire. We know that resistance is equal to resistivity times length divided by area. If we have a uniform wire with constant resistivity for each element, each part of the wire, and constant diameter, so it has constant area, then the length is proportional to the resistance. We will have E sub s, the EMF of the standard cell, being equal to the current going through this potentiometer times that portion, this resistance right here. So our situation is to have the current in the galvanometer be 0, and to accomplish that, if we have a potential drop across R sub s that's the same size as the potential drop of our standard cell, we'll have no current going through this. Question for you: why am I not discussing the internal resistance of the battery and voltage drop across this internal resistance? Hint: the current of the galvanometer is 0. Current in this branch is 0, so there is no voltage drop here. We have a potential difference here. It's matched by the potential difference across R sub s, so that R sub g, the internal resistance of the galvanometer or the standard cell, does not need to be considered. So there's one relationship. The EMF of the standard cell is current times R sub s. We're going to do a similar thing over here. Again, I sub g equals 0. The potential difference across the unknown cell will be equal to I times R sub x. And go ahead and put that up here. So it's the same process, the same reasoning. You get the EMF equals to the voltage drop across R sub x. And we're going to divide those two equations. So we have from the unknown situation, EMF sub x equals I and R sub x. EMF sub s, the standard cell, equals I and R sub s. Why is there no x or s on the currents? Why is there no x or s on the currents? Now if I bring it back to the drawing here, the current going through this potentiometer depends on the resistance of the potentiometer, the internal resistance of the top power supply or battery. It does not depend on anything down here. there's no current in this branch of the circuit, either for the unknown or for the standard cell. We do a null technique where this current is 0. Consequently, it's this loop characteristics up here that control I, and this top section of the loop is identical for having the standard cell in place or having the unknown place. The little r up here, the full value of the resistance of the potentiometer, those are constant, whether we're using E sub s or E sub x. So we can cancel those off, in fact. And if I solve for the potential of the unknown cell, the EMF sub x, multiply both sides by E sub s, we've canceled the current symbols. They're the same for both circuits. And we find that the unknown EMF is the resistance of the potentiometer section that we select, R sub x divided by R sub s. That gives us times EMF standard. That gives us the value of the unknown EMF. So this null technique, we make an adjustment on the contact point here in this potentiometer until the current is 0. There'll be an R sub s across here when that current is 0. There'll be an R sub x over here when the current is 0. And we have a relationship that the unknown EMF is standard EMF multiplied by the ratio of those resistances. This should not really surprise you because the voltage drop across here is equal to the EMF. If the EMF is larger, let's say the EMF here is larger, it's going to take a larger R sub x to match this larger EMF, and that's what our calculation shows us in the solving for E sub x, the EMF sub x. So, a null technique, we can measure the EMF of an unknown battery as long as we have a standard battery, and you should review that.